Okay, in this video I'm going to solve this problem as an example, and it says consider the set A, which is our alphabet, A through Z, with imposed alpha order, meaning alphabetical order. Determine whether the following statements are true. Explain your reasoning in each case. And what I'm going to do is I'm going to go up to the top here and just review a couple of these statements that I say here with alpha ordering on A to Z. The following are all true. B is less than C because it comes before C in the alphabet. B is less than or equal to B because B is equal to B, and therefore it satisfies less than or equal. Z is greater than F because Z is the last one. N is not less than K because N comes after K in the alphabet. Another way of writing a not less than or not less than or equal to is to put a not outside of this statement. So it's not the case that N is less than or equal to M because N comes after M in the alphabet. And similarly, because E becomes before F in the alphabet, it is not the case that E is greater than or equal to F. And so the familiar less than, greater than or equal to, less than or equal to, not less than, not greater than, all of these things have familiar sorts of meanings when we talk about the alphabet. Okay? And so the first one says, for all alphas in the alphabet, that is for all letters in the alphabet, that letter is less than Z. Well, that one's false, since since it's not the case that Z is less than Z, and Z is one of the letters. So let alpha equals Z for a counterexample. Okay, and we can disprove a for all statement by counterexample. Okay. The next one is, it's not the case that for all letters of the alphabet, alpha is less than or equal to Z. Well, it is the case that for all letters of the alphabet, alpha is less than or equal to Z. So this is a false statement, since for all alpha in the alphabet, alpha is less than or equal to Z. Okay, and it's not as easy to do with numbers as it is with letters as it is with numbers, and we might have to prove it. We might say A is less than or equal to Z, B is less than or equal to Z, C is less than or equal to Z, all the way up to Y is less than or equal to Z, and Z is less than or equal to Z. For all of these up to Y, it's strictly less than, and for the Z, it's equal to. But the less than or equal to is true, and either one of them is true, and one or the other is true in every case. So you might list them all out here to do this proof, okay? Because we're proving something for all alphas, okay? And that means that we really need to either be able to use universal generalization, which is easy with numbers because we can say, look, all the numbers from 0 to 99 are less than 100. But with letters, it may not be as easy. For part C, it says there is some letter which is between X and Z. And this is true. And we're going to prove it's true by example. Consider alpha equal to Y. Then X is less than Y is less than Z, and we're okay on that one. Okay. Part D says it's not the case that there exists a letter which is both less than H and greater than R, and that's true because H is less than R, and we can't have something which is both less than H and greater than R. And so this is true. And let's So I'll say this is true since H is less than R. If I want to prove it, I would say the proof, I would say suppose not. Suppose it's false. And suppose that there does exist an alpha in the alphabet such that alpha is less than H and alpha is greater than R. Then we could say that alpha is less than H, but alpha is greater than R. And if R is less than alpha is less than H, then R is less than H. But we know, due to alphabetical order, that H is less than R. So it's not the case that H is greater than or equal to R. So it's not the case that R is less than or equal to H. And it's not the case that R is less than H. If it's not less than or equal, it can't be less than either. And so now we have a contradiction because we have both R less than H, and it's not the case that R is less than H. So that's a contradiction, and that completes the proof because we've done a proof by contradiction then. We assume it's false and then prove that a contradiction arises. Okay, so that's this problem. Hope that helps.